Okay, good morning, everyone. Let's, announcement quiz on Monday, as usual. Topic will be mesh current analysis, and I will also post the announcement later on today, at least by evening. But again, by now, students should be aware that every Monday we have a quiz, and the topic of assessment would be the material covered in the previous week. So the topic of assessment for Monday's quiz is mesh current analysis. Okay. All right, so today we will look at the last remaining technique. And it's not a new technique per se. It's known as superposition. And if I can find, there we go, there's the class notebook. Okay. All right, let's see, what page were we on? 16, 17, and 18, 19, 20. Okay, so superposition principle applies to a, not applies, but it can be used to solve for a circuit which has multiple number of components and multiple number of sources. Independent sources, circular, not diamond. Okay. So there could be a combination of voltage sources and current sources, perhaps one voltage, one current source, two voltage sources, three current sources, could be any combination. But the point is that if it's a complex circuit, we can simplify our analysis by breaking up the circuit into smaller parts. So break the circuit into smaller pieces. And when we say piece, it refers to the source. Okay, it refers to the source. So basically, when you have multiple sources in a circuit, let's say, for example, there's one voltage source and one current source. And let's say there are four resistors in the circuit, R1, R2, R3, R4. If, let's say, both the sources are on at the same time, then the voltage that appears in the circuit and the current that flows through those resistors is a result of both of those sources working together. Right? If it's only voltage source that's active, you would have a different voltage or current appearing in the circuit. If it's only the current source that is active, you would have a different voltage and current that appears in the circuit. But if both of them are on and active at the same time, the resulting voltages and currents anywhere in the circuit is a result of both of these sources working at the same time, right? So superposition principle states that we could analyze such a circuit with only one source on or active at a time. You calculate the voltage and current in the different parts of the circuit. Then you turn the first source off, you turn on the second one. And when you turn on the second one, now you again calculate or measure the voltages and currents in the circuit. So now you have two results for every voltage and every current in the circuit. You all with me so far? And the superposition principle states that you take those two independent results, you add them up, that would be the actual voltage and current that would result because of the two sources working at the same time. All you're doing is you're summing up the results from all the sources one at a time. Okay, so let's say R is the voltage or current that appears in the circuit. Okay, that appears in the circuit. Could be any variable. Just for explanation purposes, I chose R because we primarily deal with resistors. And then you have n number of sources in the circuit. Okay, n number of sources. All you have to do is to analyze this circuit with one source active at a time. And for every single voltage and every single current, you will have n number of results. Okay, this is important. For every current and every voltage that appears in the circuit, there will be n number of results, where n is the number of sources present in the circuit. Then the actual voltage and actual current is simply a sum of all of those results. So R would be equal to R1 plus R2 plus R3 plus so on and so forth up to Rn. Does that make sense? Right? Any questions? That is the superposition principle. We have some breathing room now. Okay, the first 2-3 weeks is usually like, as first week especially is more of a refresher material from your prereq classes. Now, when we get into the new ones, we can slow down a little bit. So any questions? Everyone understand what the superposition principle is? Hopefully, yes. That is, yes. So the question being asked is, every time we solve with a source, then do we obtain a different answer? And the answer is yes. For every source, you would obtain a different answer, and then you would simply add them up. U next, and then U next after that. R is just volt. I probably should change that. It's confusing. It's just a random variable, but we assign voltage or current to that variable. So it's just an illustration example. That R could be X, Y, Z, doesn't really matter. Yes. Yes. So second point. Yeah. The second point is what I'm going to talk about next. Okay. Any other questions? Okay. So in the first point, we said that we only analyze the circuit with one source active at a time, and we turn off or we make inactive all the other sources in the circuit. So making them inactive or turning them off, what does it mean? Okay, in terms of circuit analysis, it means this. Okay, and I will show you how it works. Let's say you have a voltage source. Okay, voltage source Vs. Voltage source would be connected between 2 points. Let's call these points A and B. And the polarity of the voltage source does not matter, it could be connected anywhere. But turning it off means reducing. You reduce. So let's call this Vs. Inactive or turning it off means reducing the value of Vs to 0. Okay, Vs to 0. Now, voltage source Vs is connected between 2 nodes. If you measure the voltage across those 2 nodes, you obtain a value of Vs. The only way the voltage is 0 is if both those nodes are exactly at the same potential. And the way to implement that is by connecting a short circuit wire between the 2 points. And so we remove the voltage source and we connect a short circuit wire between the 2 points. We connect a short circuit, SC. So now if you measure VAB, voltage source Vs is 0. That's it. So you replace the voltage source with a short circuit. But the concept is we have 2 nodes. If both those nodes are connected to each other, the voltage difference between the 2 nodes is 0 volts. But the conclusion is this. This is what you should remember. When it says turn off the voltage source, it's not simply flipping off the power switch. You're replacing the place in the circuit with a short circuit wire. This is very important for those of you who are taking the lab. This is the lab for next week. So in the lab, it will state, replace the voltage circuit or short circuit the terminals of the power supply. It is not asking you to short circuit the power supply itself. It's asking you to short circuit the place where the power supply is connected, the place on the circuit where the power supply is connected. Okay, so do not short out the power supply itself, not unless you want to see a spark and an explosion. Yes. No, this is the same. It's just a technical term that we use. And as I was discussing yesterday in the lab, There's a student asking, short circuit is something that has acquired like a negative connotation to it, right? When you say short circuit, oh, there's a spark or explosion or like blown a fuse or something like that. But short circuit technically simply means it's a wire. That's it. Yes. So if you have a short circuit, so conceptual question, why does it happen? It's a simple explanation. V equals IR. I is V over R. If, what is the R for a short circuit? 0 ohms, right? So if it's 0 ohms, what is I? Infinity. So it doesn't matter what your voltage is. If your R is equal to 0 or very close to 0, then your current is infinite. Meaning if you have a power supply or even like a small battery, 1.5 volt battery, and you short out the terminals, the current goes to infinite, current takes the path of least resistance. All of that energy is discharged almost instantaneously. Okay. Everyone remember, or anyone remember Samsung Galaxy Note 7 a few years ago? Exploding batteries. What they were, so that's a real life example of what happens when you short out the terminals of a battery. So in the pursuit of making the devices thinner and thinner and thinner, apparently somebody had the bright idea to, these batteries are made out of individual cells. They are divided into compartments. So somebody had the idea of like thinning out the, walls of that compartment. And because of that thin wall, apparently because of the heat, the connection just broke through and all of that energy was released in a very, very short period of time. Energy, electrical energy, when it passes through a electric circuit, is converted to thermal energy. It's released as heat. And so if you short circuit the battery terminals, a large amount of energy, large amount of current flows through that circuit. A lot of it escapes as thermal energy, as heat, gets overheated. And depending on the energy source, if it's a small battery, it doesn't have too much, right? You might see a small spark, and all of the energy is released. But if it's a battery like a cell phone or a tablet or a mobile, smartphone, then the battery is quite large. So it'll keep releasing that energy for a longer period of time. Overheats, you might have sparks and explosions, and it blows up. And that's what happens. But once it blows up, it's basically blowing up simply means a lot of thermal energy is released all at once. That's what happens. So again, coming back to our point, we do not want to connect a short circuit at the output of our power supplies. That's why we have the current limit on there. So current limit is the absolutely most important thing to set on a power supply. All right. Does that make sense? Replacing the voltage source with a short circuit in your analysis. Okay. Current source is exactly the opposite. If you want current to stop flowing through a circuit, you should have a break in your pathway, meaning you take out the current source, create an open circuit. So if it's IS, a current source is current is flowing from A to B. The only way to make IAB equals to 0 is to create an open circuit. And thus the current I or IS would be equal to 0. Open circuit. That's it. So for superposition principle, when you analyze a circuit, what you have to do is you take one source active and you make the rest inactive. Okay, you make one source active, you make the rest inactive. And what that does is it allows you to analyze the circuit using series parallel analysis. That is, of course, if the resistors are reducible. Okay. In any case, it simplifies your circuit. You can now apply node voltage, mesh current, or as I said, if the circuit is reducible, you can apply series parallel analysis. All right, questions? Yes. Well, not quite. That's just one step in part of the superposition. Yeah. No, we still have to analyze. This is just a setup. Anything we want. We can use anything we want. Yes. KCL, KVL, Ohm's law, series parallel analysis, mesh, current, node voltage, anything. Yeah. Shall we look at an example? Okay. Okay, so here, this problem, you'll be surprised at the final answer. Determine current I2 using the principle of superposition. I2 is given to us as flowing down through R3. Flowing down through R3. Okay, so determine current I2 using the principle of superposition. Now, this is just one current I2. It is not asking for the voltage across R1, R2, or R3. Okay. You have two sources in there, voltage source Vs with a value of 10 volts, Is coming down with a value of 2 amps. Okay. Let's take a look at the circuit. What's the first thing that you see? Absolutely right. So we'll wait until people have drawn out the circuit. Okay. So as noted, on the far right, we have R2 and R3 that are in series. We could reduce that to one single resistance, right, before we begin our analysis. But let's just say for simplicity's sake, not simplicity, but let me just keep the circuit as it is. Okay, let's just solve it as it is without doing anything to it. So let's start first with Vs. I'm going to say Vs is active and Is inactive. So you draw the circuit exactly as it is without changing anything except for the sources. So Vs is active, that stays as it is. We have R1, R2, and we have I3. Sorry, R3. And then we have current I2 that is flowing through there. And what I'm going to do is, because only Vs is active, the component of I2, I will label it as I2Vs. So this would be I2 because of Vs. So another subscript in there. You can again name it anything you want as long as you specify that this is due to Vs being active. Okay. And the current source Is is replaced with an open circuit, meaning you remove Is, don't place anything in its path. Okay. So current source is gone. Now what do we see? So yeah, wire doesn't really matter, because if wire, as I said, wire is just a node. If there's nothing connected to it, and if it's just open, we can either draw it out or we can leave it in there. It would not affect the circuit. It's like a dead end street. So the question being asked is, should we leave the wire in there or should we remove it? And it actually doesn't make any difference. Even if it's in there, it's not connected to anything, so it doesn't affect the circuit at all. Okay. So this is the setup of the problem. This is the absolutely main step, superposition. After this, you can apply any technique, right? So this is the most important. How to break up the circuit into individual pieces based on the number of sources, redrawing the circuit, and setting up the problem. So the circuit's gone from 2 sources with 2 meshes and 1, 2, 3, 4 nodes to a series connection of resistances. What do we see? Right? 3 resistors in series. So I can directly write I2 Vs is equal to Vs over my Req, which is R1 plus R2 plus R3. And that's it. Vs is 10 volts, R1 plus R2 plus R3, which is, let's see, R1 is 5 ohms, 2 ohms, and 4 ohms. 7 and 4, 11. And the answer is 0.909 amps. 0.909 amps. You have to take the current direction into account. So the voltage source Vs has current going in this direction. And that current is exactly the same pathway as I2 Vs. This is going to be important when we go to Is. Does that make sense? Any questions? Okay, then let's take a look at what happens when Is is active and Vs is inactive. So let's first draw the circuit out without Vs. And current source Is is coming down. This is R1, R2, and R3. And my current I2s, actually it's not I2s, it is I2 due to Is. Okay, I2 due to Is. And now Vs is inactive, meaning we have to reduce Vs value to 0. So what do I do? Place a wire. That is the setup of the problem. Now you take a minute to take a look at it and then understand how the circuit has changed. Because the circuit has changed. So every time you try to solve a problem using the superposition principle, always take, if not 60 seconds, at least take 30 seconds to look at it and see how the circuit has changed. Okay, because now the components are connected in a way that they were not connected previously. So what do you see? R2 and R3 are in series. We can reduce those. And then R1 is connected to Is at the top node. And then if we follow the pathway, if we follow this pathway, the other end of R1 is also connected to the other end of Is. And that means it is in parallel, as was noted earlier. R1 is in parallel with Is. How about R2 and R3? They are also in parallel. So R2 and R3 can be reduced because they're in series. And then that series combination is also in parallel with Is. Okay. Take 30 seconds to look at it and understand. Let me know if you have any questions. Yes. Just I2. The question asked just for I2, but we can use this to find everything. So the question simply asks for I2. But again, we can find all quantities using this. Yeah. So we have a current source and 2 parallel connections to that current source. What technique comes to mind? KCL, yes. Division. Current division. One-step answer. So you can apply current division, or you could reduce R1, R2, R3 to one single resistance, find the voltage, and then apply Ohm's law again, find current that way. Doesn't really matter. So apply current division or series parallel analysis. Current division simply allows you to find it one-step answer. So R2 plus R3, in this case, REQ would be R1 parallel to R2 plus R3. That comes out to be, let's see, what does it come out to be? 5 in parallel with 6. So it comes out to be 2.73 ohms. Okay, you can do it. You can do this calculation on your own calculators and confirm whether you obtain the same value. So R2 plus R3, of course, 2 plus 4 is 6. 6 in parallel with 5. So 6 5s are 30. 30 divided by 6 plus 5, 11. Comes out to be less than 3. 2.73 about seems right. So 2.73 ohms. Anyone do the calculation? You get the same answer? Okay, good. So now I can apply current division. I can find I2 IS, which would be a fraction of IS. The fraction will be given by REQ divided by R2 plus R3. And IS is, what is IS? 2 amps. 2 times 2.73 divided by 6. The answer again is 0.909. But remember what I said. Current IS is not going up, it's coming down. So it's coming down this way and splitting going this way. So the current due to the current source is actually flowing up R3, not down. Okay. So current comes down here, splits in two. Some of it flows through R1, some of it flows through R2 and R3. The value of the current that flows through R2 and R3 is 0.909, but it's flowing in the upwards direction. And so, as somebody just stated, is minus 0.909 amps. And our job is not yet done. The actual IS current is a sum of IS due to VS plus IS, not IS, sorry, I2. I2 due to VS and I2 due to IS, which, as I said, 0.909 plus minus 0.909, which gives a big fat egg. Not quite fat, but. So the combined effect of IS and VS working at the same time results in 0 amps flowing through that circuit, to the right side of the circuit. All right, think about the entire procedure. Let me know if you have any questions. Remember, we only asked to find I2, but we can use superposition to find VR1, for instance. We could be asked to find IR1 or VR2 or VR3. Okay, let's take a pause. Any questions? Any questions about the process, the setup? Again, every circuit is different, so it doesn't matter which circuit it is. You can apply superposition to that circuit, the circuit will change. And then how you analyze it or find the result is up to you. Okay, and every circuit is different. What is the downside of the process? It simplifies the circuit, so that's the upside. What's the downside? Multiple, yes, absolutely. Multiple analyses have to be performed. And if you have two sources, it's still okay. If you have three sources, perhaps still reasonable. And if you only need to find one or two quantities, that's fine. But if you have more than 3, 4, 5, 6, 7 sources, and you have like large number of components in there, then for every single voltage and every single current in that circuit, you have to perform multiple analyses. And that is the obvious big downside. It is inefficient process. It's very simple, but inefficient because it takes a whole lot longer than everything else. And that's the big downside of superposition. Okay. All right. And that is actually the end of all the analysis techniques that we have studied in the class. Superposition homework only has 2 problems. It only asks for 1 quantity each. It won't even take like 30 minutes to solve it, but I'm going to go over. I will go over the slide. So page 36, homework 11. The 2 problems are 2.95 and 2.97. Both of them have just 2 sources each. 2.95 only asks to find the current IS. Okay, current IS. This is the same circuit that you saw in, was it mesh current or node voltage? Node voltage, I think. The current direction IS, it simply means you are measuring, if let's say you had a meter to measure that current, then you're simply measuring the current flowing in that direction. Current flows from positive to negative, so arrowhead is always positive. I mean, arrowhead is negative and the tail is positive. So you're connecting a meter with its terminals connected as the sign shown, right? Tail end is positive and arrowhead is negative. That's your meter terminals. That's all it means. So you calculate, as we did for the previous example, and then you look at the direction of the current. If it's opposite, then you just put a minus sign next to it. So in this case, you have 1 voltage source and 1 current source. A voltage source is active and current is inactive. This is gone, right? Current source is gone. Only voltage source is left. You can ignore the ground because the ground doesn't actually affect the circuit operation. It will affect how and where you measure the voltages, but it doesn't affect the currents that are flowing through the circuit. Okay, ground is just a reference measurement. Think of it in those terms. What do you see about R2 and R3? So if you take a look at R2 and R3, they are connected at the bottom node. This is no longer part of the circuit. You would redraw the circuit, obviously. And R2 and R3 are connected at the bottom node. So they're connected at the bottom node. They are in series because there is no other component connected to that bottom node. And then those two are in, anyone? The relationship with the 10 volt source would be, you can actually flip the circuit on its side. So I'll draw this out here so that students And I like to tell students, redraw the circuit as many times as you need until it starts to make sense. And that's what I used to do as a student. If it didn't make sense to me, I had a hard time figuring it out when I first started. I would just keep redrawing it in multiple ways. You keep redrawing it, but you keep track of each and every node. You keep track of each and every component. And that helped me. And I think several students in the past also told me that it helps. So you redraw the circuit as many times as you need until it starts making sense. You can label the nodes, and you redraw the circuit and you analyze and you figure it out. And this is IS1. And then the circuit for current source would be, let's see. This is the reason I wanted to draw this. If the current source is active, voltage source is replaced with a short circuit. Oh. What do we see now? Bless you. Allergies? Mine are really bad. Can't function without Zyrtec, unfortunately. What do we see? Current source is active, voltage source is inactive. Voltage source is replaced with a short. That short circuit or that wire is in parallel with a resistor R1. R1 does not matter. If you're driving down the street and you have two pathways to take, street number 1 has construction and debris and traffic, and street number 2 is completely free of obstruction, no traffic at all. You would obviously go down the path of least resistance. So if R1 has a value of even 1 ohm, doesn't really matter because the short circuit R is equal to 0. So the value of this short circuit is 0 ohms. So everything goes down that pathway. Anything that is connected in parallel with a short circuit wire is effectively redundant. It is removed from the circuit. It has no effect whatsoever on the circuit. That's the concept that everyone should remember. Okay. So again, circuit changes in fundamental ways. So when you perform your analysis, you have to take a look at it for 30 seconds, for 60 seconds, let it sink in, and then start to analyze it. Okay. So in this case, again, if R1 is effectively not part of the circuit anymore, what do we see? R2 and R3 share the same 2 nodes, and they also share the same 2 nodes with 1 amp. Okay. Is that enough of a hint? That's actually more than half the solution. And you only need to find 1 current source, okay? So, and then this is, again, rather straightforward. Actually, no hints required. You have 2 current sources in there, and you just have 1 active at a time, and it's rather straightforward. Okay, so again, practice these problems. I think I might add like a few more practice problems to this, not for credit, not for extra credit, just so that students can actually take a look at the circuits and practice if they want to. So maybe some advanced level circuits. So if you need, you can use these circuits to actually practice for node voltage analysis, mesh current analysis, and superposition. All 3 techniques can apply equally to all of them. Okay. All right, questions? Any questions at all? Yes. Yes. So the question being asked is, if there are 3 sources, then would 2 of them be inactive? The answer is yes. If there are 4 sources, then 3 would be inactive at a time, and so on and so forth. The main point is only 1 source is active, the rest would be inactive. That's the main point. Okay. All right, now we come to a very important concept. So again, this is the end of the analysis techniques. Okay. We will not, again, the analysis techniques were based on KVL, KCL, and then superposition. Again, it's not a entirely new technique, right? You're simply setting up the problem to simplify it, and then you apply any technique you want, right? You have KCL, KVL, Ohm's law, current division, voltage division. Those are the primary techniques. Everything else is a simple concept, and you apply those techniques to solve. So now let's say you are an engineer and you're working with some large complex circuit. Perhaps it's a small circuit board that goes into a machinery, and you need to find the voltage across R6. Okay, you're trying to find the optimal value of the resistor R6 so that the voltage across R6 fits within a certain spec. So what do you do? What techniques come to mind if you wish to find VR6? So yeah, certainly node voltage analysis, mesh current analysis, or superposition. Any technique, right? Any technique. You go through your analysis and you realize the value is incorrect, or it doesn't fit. The voltage VR6 does not fit within your spec. So then you try a different value. So you would, you do a first analysis with R6 with a value of, let's say, 50 ohms. It doesn't work. You perform a second analysis. You go through the whole procedure again. This time R6 is perhaps 40 ohms, let's say, or maybe 30. That still doesn't work. So maybe you go through another analysis, third, and you keep applying values, perform multiple analysis techniques until you actually find a value for R6 that works, right? That works for your spec. So what are we doing? We are performing multiple analyses, right? Multiple calculations to determine an optimal value. Well, there was a French telegraph engineer in the late 1800s by the name of Leon Charles Thevenin. He postulated a theory that said that instead of performing all of these analysis techniques all at once, multiple times, we could analyze a circuit only once without R6 part of the analysis. Okay, and that theory that he postulated came to be named after him. It is known as Thevenin theorem. Okay, Thevenin theorem. And the theory he postulated was you could take the entire circuit outside of R6. Okay, outside of R6. So R6 would not be part of your analysis, and you could represent the entire circuit. That is a linear circuit that comprises of multiple sources, multiple resistors. You can represent it by a single voltage source in series with a resistor. In series with a resistor. So you could take that large circuit and you could represent it as a single voltage source in series with a resistor between the terminals where R6 was connected. Okay, where R6 was connected. So again, R6 is not part of the analysis. And I will show you how and why it would be beneficial. So Thevenin theorem, Thevenin circuit is a very important concept. It is not a new analysis technique. Let me be clear. It is not a new analysis technique. It's a concept. The techniques that you would apply are the same ones that we have learned so far. Okay. If you've looked at your if you looked at the final exam, this is a 30-point problem in the final exam. It has multiple parts. Every part is either 5 points or 10 points or 2 points. It tests everything from chapters 1 and 2. Okay, so outside of R6, you can represent it with one single voltage source and one single resistance. Now, if you have this circuit on the left, the out plus and out minus is nothing, is simply the label. Okay, out plus and out minus is just the label. So don't worry about that. If you wish to find the voltage through R6, what technique could you apply? Sure. You apply KVL. You can find the voltage by applying Ohm's law, or you simply apply voltage division, and you have a one-step answer. Now you can simply program whatever value for R6 you wish, and you can calculate it as many times as you need. One-step answer. The most important point is that outside of R6, the value of this voltage and this resistance does not change. Okay. If the value of all of these components in the circuit remain exactly as they are, which of course they would, then the value of the voltage and the resistance in that equivalent circuit do not change. They remain the same irrespective of what the value for R6 is. Again, we are analyzing the entire circuit outside of R6. Yes. I was just about to explain those. Yeah. So this is an equivalent circuit because, well, again, it is equivalent to a larger circuit, right? So the voltage in there is known as Thevenin voltage. And the resistance is known as the Thevenin resistance. Okay. Sometimes the notations might change. It could be VTH uppercase, or it could simply be VT. This could be RTH or simply RT. But if you see this in a circuit and a question, you should recognize it is talking about a Thevenin voltage and Thevenin resistance. Okay. Thevenin voltage and Thevenin resistance. Once you analyze the circuit once, only one time, then the resulting VTH and RTH do not change. And you can find the value for the outside voltage as many times as you need. Few decades after this theory came about, there was a engineer working for Bell Labs. He was working in audio applications. Audio applications use a lot of current sources for theoretical analysis. And so he found, his name was Edward Norton, like the actor, but not the same guy. So he postulated the theory that said that you could take that large circuit and represent it as a current source instead of a voltage source. Okay. Instead of a voltage source, you could perform the same analysis without R6 and represent it as a current source in parallel with a resistance. And that came to be known as Norton's theorem. IN is the Norton current. The resistance is still the same. It's still RTH. Sometimes to distinguish, some people like to use RN, Norton resistance, but it's not actually Norton resistance. It's simply the Thevenin resistance. Okay, and then again, the output terminals, we have R6. So this is a very important concept in electric circuit analysis. Please think over this, right? And we'll look at it next week. A real life example of this would be starting up your vehicle in very cold weather. Okay, in very cold weather. So let's see, it's 10 o'clock. We'll end class here today. I will see you all on Monday. Have a good weekend. Again, superposition homework is due. It's due on Sunday night. But again, if you want, you can knock it out like today itself, and then you can have your weekend free of circuit analysis. All right, we'll see you all on Monday.